This video lesson is going to go over variability and spread of data in our statistics unit. So the first thing we're going to talk about, in our last lesson, we talked about how to create a box plot and the shape of the box plot, but we did not talk about the actual information that is shown in our box plot. So I'm actually going to pull up my next slide here while we talk about this as well. There we go, that's a little better. So our minimum is our lowest value. That's shown by this either dot or vertical bar in our box plot. The next vertical line we see is our quartile 1. The next line we see is our median, quartile 3, and then our maximum value. So each of these pieces, those vertical lines that are shown, is one of what's called my 5-number summary, because there are 5 values that help us make our box plot. Another important thing when we're looking at a box plot is that there is 25% of our data in each chunk, so to speak, of our box plot. So here, this whisker is 25%. This part of the box is 25%, this part of the box is 25%, and this other whisker is 25%. So 50% of our data is held in the box. So the whole box itself is 50% of our data. And again, 50% of our data is on both of these whiskers. So if you had your numbers lined up in numerical order, I would find the middle first. That's my median. And then between the minimum and the median, I find the middle again. That's quartile 1. And then between the median and the maximum, I find the middle again, and that's quartile 3. So really, I'm breaking down my data into 4 equal chunks, which is where this 25% comes from. 1/4, 1/4, 1/4, 1/4. So we're going to actually go through an example in a little bit and create a box plot and do some analysis with that box plot. But before we do that, we do need to talk about a couple other things. So variability is the spread of our values in a distribution, how different they are from the mean, how different they are from each other, how different they are from quartile to quartile, and things of that nature. So there's a couple ways that we can look at variability. We're going to talk about range. IQR stands for inner quartile range, and then standard deviation is one other method that we're going to look at with this variability. So let's talk about what all 3 of those things mean, and then we'll do an example. So when we're talking about range, I'm looking at the difference between the maximum value and the minimum value. Biggest and smallest, how much space is in between. For the inner quartile range, I'm looking at, so this is, max minus min. And here, this is Q3 minus Q1. That's inner quartile range. Now, the range in the inner quartile range can be used for any shape of data. It does not matter if it's skewed or normal or uniform. Those can be used, for any range of data or any spread of data. Standard deviation, however, is only really used for a set of data that is normally distributed. And if you think back to yesterday, normally distributed data follows that bell curve shape where there's a very clear peak in the middle, and we are symmetric on both sides. So this would be the mean, the median, or the mode. They're all going to be that center peak. And then we have half of our data below and half of our data above. It's that symmetrical property of this normally distributed data that's important. So now when we're talking about standard deviation and what that actually means, standard deviation is a way that we can explain how a value differs or relates to the mean. And we're going to look at standard deviation. We're going to calculate it in just a second so it will make more sense. But if I'm looking at this standard curve or this symmetric curve, and I talk about one standard deviation from the mean, let's say it looks about like this. So this is one standard deviation below, and this is one standard deviation above. The vast majority of my data lives in this chunk where I am one standard deviation from the mean. This is 68% of my data. So if you have a standard deviation that is a small number, that means all your data is really smushed together and it's really close to that mean value. If I have a standard deviation that's a really large number, that means my data is really spread out. My numbers are much different than the mean, and my curve would be a little bit more flattened because everything is really spread out. So that's really, in Math 1, that's what we need to know about standard deviation. But let's play. Let's actually do some calculating. So here, this is my set of data. Go ahead and hit pause. Go to your Desmos graphing calculator, make a list, and put these numbers into that list. So I've already done that. Here is my list. And just like we did yesterday, I'm going to open up my keyboard and go back to functions. And I'm going to be under statistics. And the first thing I want to do is actually find my values for my 5-number summary. So I need the minimum and the maximum. I need the median, and I need quartile 1 and quartile 3. And I'm going to jot these down as we go. And then I'm going to go back to my document camera and show you how I would put this together. So the first thing I'm going to do is find the minimum. And I need to tell Desmos that I want the minimum of my x1 value. And because I'm going to have to use this x1 a lot, you can see I just highlighted it. I'm going to copy and paste just to make my life easier. So the minimum value of this list is 5. I'm going to do the same thing to find the maximum. You can go to functions and click max, or you can just type it into your function. So that's my maximum, 53. I need the median. So my median value of x1 is 22. Now you could take this list, write it in numerical order, go through and cross stuff out and find the median, go through and cross stuff out and find the quartile 1. But when I have Desmos, it makes my life a lot easier, just type it in. All right, so when I'm finding the quartiles, I need to tell my computer, hey, I'm looking at list X1 and I want quartile 1, and I do that by typing in a 1. So quartile 1 is 12, and I'm going to do the same thing to find quartile 3. So quartile 3 is 36. Now I'm going to show you the box plot on here just so that we can see it. I don't really need to change anything. All right. So here's our box plot. I can see that my right whisker is a little bit longer than my left whisker, but for the most part, the box looks pretty symmetrical. So this would be my minimum. Here's my maximum. Here is my median, quartile 1, and quartile 3. So if, for example, it was a question that was matching a box plot to a set of data, I would go through and calculate my min, my max, the median, and both quartiles. And then I'm going to check and see what box plot actually has that information. I can guarantee you they're going to give you the same minimum and the same maximum on an example or on a answer choice or two, but they're going to mess with the quartiles and the median. So you have to make sure you pay super close attention to all 5 vertical bars on your box plot. All right, so let's see what happens when I take out this really large number of 53. So I'm going to come in here into my table. I'm going to take out 53. So let's go look at the minimum didn't change, the maximum changed, the median changed, quartile 1 didn't change, but quartile 3 did change. So why did the minimum and quartile 1 not change, but the other 3 values changed in my box plot? Well, I'm still going to have a middle or a minimum value of 5 because I didn't change anything about the minimum. I only took out one number. So I shifted down a little bit, but let's see, my median before was 22 and now it's 18.5. So I did shift down a little bit, but if you look at your list, I don't have an actual value of 18.5 in the median. So 18.5 and 22 have kind of swapped out with each other. So I took 22 out of being my median and replaced it with 18.5, which is not an actual value in my list. So really, I haven't changed anything about the bottom half of this data by taking out 53. But I have changed the maximum because I took out the highest value, which has to change my quartile 3. So now you'll notice the box looks a little bit unevenly distributed. This right side is a little bit bigger, but now the whiskers look a little bit more symmetric than they did before. Okay, so that's our first example. I'm going to come back to my screen here. Let's say that they asked you for the range, and I'm going to go back to my original data set. If they're asking me for the range, they want the maximum minus the minimum. Well, that would be 53 minus 5. So that would be a value of 48. That means that my data spreads over 48 units. If they asked for the interquartile range, that means I need to do Q3 minus Q1, which would be 36 minus 12, which gives me a value of 24. So this goes back to my original data set. I still have 53 in my data set. This was my original. So what this value means is the box itself covers 24 units. This means the whole box plot covers 48 units. So that's my box plot information. Now I want to go and look at this example. This is different travel times in minutes. So go ahead and pause your video. Enter this into a different list. You can just add a completely new table and get rid of that last one we had. But like I said, pause the video, make yourself a list, and we're going to work with this data set. So I have already done that. Here is my list. Make sure you're double checking that you have the right information in your table. Otherwise, it's going to be very different than what I have. So for this one, what we're going to look at is standard deviation. So the two things that I need are the mean and the standard deviation. Well, I go back to functions. Both of these can be found under stats. And I want to find the mean of my list X1. So the mean is 41.2, we'll say 41.24. When we're dealing with statistics, the more accurate you are, the better. So I usually tend to go with 2 or 3 decimal places when I'm doing statistical analysis. And I'm going to come in here and do standard deviation. I'm going to go under function, and we're going to use standard deviation P. What that means is the information that I have in my list is a complete list. I am using the entire list, this entire chunk. It represents everything I need. It's the whole population of my data. And I'm going to put in X1 and I'm going to hit enter. So this tells me 15.58 is my standard deviation. So what this means is that the biggest chunk of my data is within 15.5 units from my median of 41. And just so that you can see what this means, I'm going to do my histogram. Let's do my data set of 1, and let's say I'm going to do 5, and I want my left. Let's say I'm going to do 3. Trying to make it look as normal as possible. All right, normal-ish. So here's my distribution. You'll notice this 90 looks like it's kind of way out in the boonies, right? Doesn't look like it fits in very well. So just coming back over to here really quick. So if this is my median, or excuse me, my mean of 41.24, and here's my little curve. Ooh, boy. Let's pretend that the peak is actually in the middle. Meow. Close enough. So here's the middle, right? The biggest chunk of my data is 1 standard deviation above or 1 standard deviation below. So to find this one, I'm going to do 41.24 minus 15.58. So 41.24 minus 15.58, which gives me 25.66. And then for this one, I'm going to do 41.24 plus 15.58. Which gives me 56.82. So I know this is the median, and a good chunk of my data, 68% to be exact, lives between the values of 25.66 and 56.82. What would happen if I took 90 out? Let's see. I'm going to go back here to my list. I'm going to search for 90, which was somewhere in the middle. There it is. So I'm going to take out 90. Here's my new list. Let's come back up here. Well, without 90, it's really changed my data. My mean is now 38.8, and my standard deviation is now 11.4. Taking out that gigantic number that looked like it was probably an outlier has dropped both the mean and the standard deviation significantly. So coming back over here, here's my mean of 38.8. Am I missing some? Oh no, that was it. Okay. So the lower one is going to be 38.8 minus 11.4. So now 27.4, and 38.8 plus 11.4 gives me 50.2. So now looking at how taking 90 out has changed my data set. My values are closer to the mean because my standard deviation is smaller, and my mean is now smaller. If you think back to yesterday, remember we talked about how outliers drastically change the mean. Now I know it doesn't look that drastic here. 38 and 41 in the grand scheme of things aren't that far apart, but that is a big change when I talk about taking out just one number. So now if I look at my curve, my numbers are smushed closer together because this is a smaller range than here. So if I'm talking about how my distribution would be considered for my driving times, for example, in this case, this 90 is really skewing my data and making it look like the majority of our driving times are higher than they actually are. So some other questions that you might be asked. You could be asked using mean and standard deviation, who had a faster racing time, for example. So using this, if these were race times, well, I would say the person who looks like they might have a faster race time would be the person who has a higher spread in that first standard deviation. This is a much larger number than 50. So I would say this person, this first set of data, they probably have a little bit of a faster drive time. Another thing you might be able to might be asked to do is compare some 5-number summaries. Who has a bigger interquartile range, who has a larger maximum, larger minimum. If the interquartile range shows a greater spread in the box. If the interquartile range is large, that's probably a larger spread. If the interquartile range is small, then that spread is probably pretty small.